you, and then you can go. So I will push the button now.
All right, so everyone's probably reeling in from the ICML deadline, but now for today's seminar, we're hosting Animesh Garg, who is an assistant prof at U of T, and he's also affiliated with the Vector Institute and also works part-time as a senior research scientist at NVIDIA. So just for a bit of career background, he first did a master's in Georgia Tech and then did another master's and PhD at UC Berkeley. But what's so interesting, and the reason we've particularly invited Animesh, is his group works in a variety of areas, not just robotics, but ranging from deep learning theory to applied and a lot of other things. And his talk today is titled "Building Blocks of Generalizable Autonomy in Robotics." We'll hear from him soon. Over to you, Animesh.
Thank you. Thank you, Krishna and Liam, for organizing this very impressive set of speakers and series. And this is definitely very exciting for me to be speaking here today. And of course, a number of you might be coming off of ICML, so hopefully I'll keep it very lightweight. So fun. So what I wanted to do today, and I want to preface this, is I have been working on this problem of generalizable autonomy for at least 7 years. I have been very much inspired by ideas of what I used to call out-of-the-box autonomy. When we can actually have a robot product that you can buy from company X, and you can just bring it home and it works. The same way your iPhone works out of the box. And as a roboticist, that feels like a dream, actually. It is so interesting to think about realistic robot systems that would work in unstructured, unknown environments of potential consumers that you do not know yet. This is a problem that I've been working on for a few years. And last year, or about 2 years ago, I presented a version 1 of this talk, which was update up until 2019. So the game for today's talk is going to be update 6. The talk might be rough around the edges, but hopefully will give you interesting ideas and interesting questions and might incite some interesting discussion and potential collaboration. Okay, what is the problem? The problem is we want this sort of out-of-the-box autonomy. We want it today. What do we want it to do? We want it to do a variety of things: vacuuming, cleaning, sweeping, cooking, laundry, and whatnot. Not only that, we want it to work outside of your lab conditions. We want it to do this in my home, your mom's home. It should work with arbitrary set of tools. Maybe semantically they are the same, but well, mops appear in many different ways. And perhaps they need to extend their ability to solve problems beyond what was shown. Maybe you had a large dorm party, so the sink is full. Maybe your child actually drew very much stuff on the wall, so that needs to be cleaned. Or you forgot to do laundry because of ICML, so now you need to do all of that. So what's the problem? So the problem really is that we need to build hardware systems that can operate in real-world environments and handle all of these interesting open-world unstructured. Now, one might argue that this has been the goal of AI ever since its inception. AI was conceived in 1957. We had first robots in 1961. And ever since, we have wanted to build this sort of robots everywhere kind of thing. And I would argue we have made a lot of progress, actually. So this is a video from not too long ago. This is a Christmas video produced by Boston Dynamics, where you see 2 different types of very impressive robots doing some very impressive, well, motion. The trick or the key here is all of this motion is choreographed. This is known structured environment, which is operating in a known world, doing expected things. Now, this is not to say that this is not impressive. This is immensely true. But the problem is, if you take any of these systems and put it in a mundane environment where it has to do chores, It turns out that building real robots with real perception in real environments is really hard. So now what is the key problem? The key problem is, how do we achieve algorithmic generalization where the notion of generalization can extend to new objects, new scenes, new semantics, or perhaps new task goals, so you can actually operationalize this problem over more compositional problems. So the core idea or the core effort of my group is to figure out or to study and understand what are the building blocks of this generalization. I argue that the solution to this sort of unstructured problem is a two-step process. The first step is to figure out how to specify tasks and how to do tasks in particular domains. The solution to that might involve some mechanism of imitation. We need to specify the task. This specification can be visual, can be language, can be kinesthetic. In that setup, the system or the agent needs to perform this task in a data scarce setup in that particular domain. Therein, we need algorithms which can take this idea or this concept and generalize it to new task domains with novel environments through a notion of self-practice. You are not going to be able to talk to get data for every possible chair in the environment or in the world. And to do this, I argue we need structured inductive biases in how we make decisions, algorithms, and causal modeling to understand how to expand what we know to new tasks. So these will be the two core building blocks, according to me, to build this algorithmic generalization or pipeline for algorithmic generalization. Now, as roboticists, we have to really think about multiple interacting problems. Robotics is immensely diverse. And the question really is how learning interacts and affects not only decision-making and control, but planning, perception, and how we can ingest large amounts of data. I've been working on both core methods in machine learning for robotics across all four of these topics, and trying to find applications and transformative methods in applications for robots in personal and home setups. We have also been looking at manufacturing and service robotics, and we have also been thinking about how these ideas can also be applied to healthcare and safety. Over the years, a lot of the work that I've done has been inspired and motivated by problems across these domains, and have also been applied to and evaluated on a number of different robots, starting from surgical robots with autonomous surgical subtasks. We have more sort of manufacturing and manipulation robot arms. And then of late, we have also been looking at applying these methods to legged locomotion. But for today, I'm going to focus the effort primarily on manipulation as an example. And I'm going to talk about how the ideas from structural learning or inductive biases and causality affect the problems along this horizon or along the spectrum of starting from low-level controls to increasingly more planning or perceptual, increasingly more planning-based compositional tasks. Then we talk about perception. And then finally, we have to think about how we might actually solve these problems in robotics with new, larger scale data. So let's start with visuomotor skills or control skills. Before we get into this, let me introduce a very common sort of paradigm of solving these tasks that is popular currently is reinforcement learning. The core object here is an MDP or a Markov decision process. Many of you may already be aware of this, but humor me just for a minute. You have basically a setup of an agent interacting with the environment. And the usual stuff is you have a state space or an observation space. The agent makes decisions in action spaces. There's an environment that evolves with some transition model, results or emits some reward model. And then there's a time horizon you need to solve the problem by. And what you're really after is some sort of decision-making function or policy, pi, that is a mapping from state to action that optimizes for some cumulative result. So that's the problem setup. In more current setups, this framework might look something like this, where you have a state with image input, some deep network or function approximator, which is your policy. Output may be torques, because we are talking about manipulation, but it doesn't necessarily need to be. Some low-level actions. And then there's a learning rule. There are many learning rules. This is particularly just a value function-based method, but it doesn't have to be that. The interesting question that I'm trying to understand is, if we think about this anatomy of deep RL process today, the question we need to ask is this as is the final solution? Or are we actually leaving a lot of structure on the table? So the first set of questions that I want to ask is, can we improve this paradigm? And what I'm going to talk to you about today is, on all four directions, there's a lot of structure that we are not right now analyzing, particularly for robots. So let's start with states first. Should we operate on states, or should we have some state perception model? Particularly for robotics, how do we get this sort of structure? So let's look at a very simple task. The task is some sort of peg insertion. This peg insertion manifests itself in terms of, let's say, putting plugs in sockets, or putting keys in doorknobs, or putting bulbs in sockets either. And the whole idea, or the core idea of the task, is you have to align and insert. Fairly simple to understand, but it's a fairly general task, and we actually do not have general purpose robots that can solve all variations of this task. How would someone else or a person right now do it? They might get multimodal information, maybe vision and touch. It could be other modes as well, but for now, let's limit it to vision and touch. They might convert this perceptual input to a number of task-relevant information representations. It may be poses of objects, it may be geometry of the scene, understanding of the forces, the frictions. And it's not necessary that you explicitly have to estimate these correctly, but the notion of this may help you generalize better. Given this information, you can come up with a controller that tells you what action to take. Now, what would that look like if you were to design an algorithm? That might look like observation input to your policy function and output torque. What we are asking is it better to have structure or some sort of inductive bias to handle this kind of input before you pass it to a policy? We want to learn a function G that is independent of the task to operate in this way. How do we do this? We want to learn some sort of multimodal representation of the task itself. So we start with a very fundamental task of this peg insertion. We design this system with three inputs: RGB, force and torque, and robot kinematics, where the robot is basically aware of its own joint. The interesting trick is, we don't tell the robot that the peg is not going to be round always. So the peg can be different shape, but the peg's shape is not actually encoded in the input. You can, of course, say that this is a one-hot embedding, but then the system can learn to be differentiated by that. So the system or the representation needs to figure out what is the domain you're operating. How do we learn such a representation? So what we do here is, it's an autoencoder style representation, but instead of reconstructing the full state, we can basically learn to do this representation such that there's an information fusion, which is a module that will do the heavy lifting of perception, if you will. And then there will be a decoder, which can decode to something that is task relevant. The task relevant part will often be lightweight. That is the thing that you will actually use at inference time when you do policy learning. You want to learn this sort of encoder in a manner that captures all of the information that will be necessary for a number of tasks downstreams. So what we do here is we do self-supervised data collection. In this setup, we are collecting the RGB information, the RGBD information, computing optical flow, which we can compute analytically, and also just recording the forces on the independent. Now, what we do is we train jointly an encoder to do these three things. We ask the model to predict action conditional optical flow. So predict where the position of the robot will be in space. Notice this is better or easier than full image prediction, because then you have to figure out how background behaves. Another question we can ask for the self-supervised model is just predict based on all of the information that you have, will the next step be in contact point? And finally, if you jumble these videos across time or jumble these sort of observations across time, can the system figure out, is this sort of a coherent or a kosher observation? So being able to say that this doesn't look correct, like I'm observing something when I'm seeing touch, but I'm not actually touching it, should not be correct. So just being able to learn this in a manner results in a cross-modal representation that can, one, fill in for other modalities if one of them is missing, results in a robust representation that can capture sufficient features. Now what we do is we take this representation and we can freeze the encoder model while we train the policy. Interestingly, the policy is a very small network that can be trained directly on the real robot. So what we see here is, I'll probably just jump the video because this is a long one, where the policy that we learn qualitatively is fairly robust. There is no calibration of the whole to the robot, and the robot can actually figure out how to solve this task in a manner that is essentially end-to-end control, and feedback is happening through visual modalities. More interestingly, actually, what we see is in about 300 episodes of real robot training. So notice there is no sim to real business here, which is about 4 hours of training. You can get to 90% success rate on some cases and 75% success rate in other cases. This is the obvious result that I wanted to show you before interesting results. Here, we start with a triangle peg and a triangle hole. The policy in both are trained on the same setup. And what we see here is, if you get more information, as in image, force and image, your performance improves. This should not be very surprising, of course. The more interesting stuff is, we wanted to ask the question, what really transfers? If I train my representation and policy on the same peg and just take it to a different peg, will that transfer? We see that actually doesn't. You start to fail a lot more often than not. But if we flip the thing and we say, I learn a representation on triangle, but do the policy learning part only on a square representation, then the representation did not need to be on this new environment. This basically tells me that I can have a general purpose representation for these kind of tasks, while the last mile of policy learning can be done after the fact. So this is important for understanding that we can do data collection, we can do a lot of representation learning up front and fix it, and then do task learning at the end. This is very similar to the kind of successful results we are seeing in other domains where you can do representation learning up front. Think GPT, where language encoding happens up front, and the final tasks is the last layer that you can add on top. Of course, this is not at that scale, but really that's where we would like to go.
Can I ask a quick question?
I have a quick
Absolutely.
Oh, maybe we both have the same question. Let's see. You go.
All right. Yeah. So I was wondering if you consider learning representations over multiple shapes as opposed to like doing the other way around. What I see is you're learning representations, let's say on triangle peg, and then learning policies over a combination. But what if you flipped this, like learned representations over a range of shapes? Because that's presumably cheaper.
Yes, in principle, you could do that. I think in this particular case, we just wanted to show that once you do representation learning on particular setup, it can generalize to a completely new setup. Of course, in principle, if you randomize the data for representation learning, you might actually have even better representations that might generalize. But that was an experiment we did not run at the time. But I would argue that in principle, it could result in more robust representations. Agreed.
Thanks.
Liang, was it the same question or something else?
Not quite. So okay. Do you mind going back one slide? Yeah, so I guess I'm a little surprised at how poor the success rate is for the testing on square, since you would have thought that kind of the actions that are needed to solve this task are kind of exactly the same regardless of the whole and the end effector. So do you have some intuition about why it fails so much here?
It's a very interesting task. It is like deceptively simple and it's easy to fail because the whole point is that you don't succeed unless you have aligned and insert. So the alignment part is actually shape dependent. So you can get to the whole very easily. So you will basically get a lot of the sort of part of the task where you would basically be in the right neighborhood. But then at the end of it, the policy actually needs to do local sort of alignment because the actual whole, you don't actually have a calibration of it. So you don't actually know the pose of the whole explicitly. You are doing this through image-based feedback. So if that part is not known, you may sort of fail. And one of the things that is not insert in here is if I rotate the squares, right, in non-standard rotation. So let's say I rotate this thing 30 degrees, then the performance would fail even more because then what happens is accidental insertion becomes even harder because you actually have to rotate. So that's where sort of it fails. Of course, we found that if you increase the tolerance, this would become easier because accidentally inserting it becomes more likely.
Amazing. Makes sense. Thanks.
Cool. So the next step I wanted to ask was, we just looked at, oh, you can have state representations and they can improve performance. Now let's flip the version and let's look at the output of your policy. Your policy output is assumed to be thought, but why? There's nothing special about it. So let's look at another task. The task can be, this time around, wiping a table. So now if I wanted to do a simple wipe task, I might build a system with my inverse dynamics system. I might write the robot's dynamics, write the equations of dynamics, and build a task model. But the problem with this kind of approach is often you need to build particular domain-specific perception, and then these sort of task trees. You have to basically define behavior tree. You do particular gains here. When you touch the table, you do particular gains, that kind of stuff. Now, of course, deep reinforcement learning tells you we can solve this problem end to end, no worries. But I don't have to tell you that that kind of method is either very slow or is very brittle. So it can fail if training and testing have any sort of variation. The question we were sort of motivated by is there any best of both worlds here? It turns out there is. If you really think about this problem more from a functional transformation, you can think of the input to still be an observation, but the output space doesn't have to be an observation. I know the robot model. Anything that happens in the task space of the robot model can then be converted to the robot actions, let's say torques, through a known deterministic mode. But this by itself is not necessarily new. This is something that we have not known since 30 years or so in operational space control. The more interesting part is it's the change of impedance gains or the scheduling of impedance gains that captures the task behavior. You want to give the ability to schedule these gains to the policy. So instead of just having positions, you actually add gains in the policy as well. So policy can decide where the end effector needs to be and in what dimensions and at what level of stiffness should it operate. This is basically a best of both worlds kind of setup where you can utilize the model and at the same time operate without explicitly specifying the task behavior tree. So what you see here is in the inset is a figure that the robot sees, input image. And what we're going to do is just compare simple performance. The only thing to note among all of this is the bottom line, which is basically image to torque, and the top line, which is end effector variable impedance or vices. And what we noticed is that by changing the representation of actions, you can get very good or efficient performance very quickly, even in image to control tasks. Interestingly, because you are able to decouple this, you can swap the morphology. So you train on Panda and then you transfer to Sawyer. There is no training at all. Of course, performance drops because morphology changes in many ways. But the fact that the performance out of the box on a new morphology is close to 60% is already impressive. Even more interestingly, you can take the same system and now replace the outer parameters of fsim with an freal. And you can now transfer sim to real. Again, no dynamics randomization, no funny business, as it is on a real robot, and get 80% success out of the box. I think that is very impressive for image-based control tasks, that understanding the right biases and the right structure in which input and output space should operate in allows you to get such efficiencies. Now, the obvious next question we have been asking ourselves is, okay, in this particular case, we were able to specify the right task space. Can we actually learn the task space based on the task itself? So this is a paper that is currently under review, but I do want to sort of motivate this. Any sort of task will have an implicit task space that will lead or induce a manifold. We are interested in discovering that manifold so that all of the exploration happens in that manifold. How do we do that? You can do this through, again, autoencoder style architecture, but autoencoder architecture, which is, let's say, dynamically consistent. So what you say is, I will learn a representation of actions such that using that action in latent space results in, 1, reconstruction of the action, 2, results in the same transition dynamic. So it's equivariant in this latent space. You can do this learning both in an offline and an online setting. So in an off-policy setup where you have a data set, and also in a setup where you're simultaneously learning the policy to do this. So you're learning a representation of this MDP or latent MDP, and then learning a policy in this latent. So I'm going to show you this result on 3 different tasks, or we applied this on 3 different tasks: the door opening, moving to points, and then wiping task again. Interestingly, what we see first of all is, if you do an original action space training, so PPO is trained on an original action space versus a representation that has been learned on an original action space. Very early on, due to the right action space, you discover reward. Because the new action space only does movement in the right latent space. So even random actions discover reward very quickly. That's one. And of course, after some training, you can solve the task. But interestingly, if you notice, the way laser action space solves the task is much more what you would call natural compared to a robot sort of ranking around in space and solving the task. Of course, laser solves this task much faster. Second, interestingly, this can do online training as well. So you don't actually have to do training completely offline. So you don't need to know the task up front. You can learn this action space during. And again, the same thing happens. You learn the right action space, so the robot is very smooth. And in this other case, applying SSE, the robot diverges at some point of time and cannot actually open the door. Any questions so far? If not, let's continue. So the next thing that I wanted to ask in this sort of question of, or series of understanding this diagram, we have been told that we can do deep reinforcement learning, but if we really think about deep reinforcement learning, the deep is not really very deep. It's 2-layer MLPs. Now, the question is, why? One argument can be, oh, but if you have very deep layers, you lose information. If you lose information, you cannot do very much. So simply just adding layers to your model to add capacity may not be sufficient. So this is an idea which seems very intuitive in hindsight now, is by adding different kinds of structure that add, let's say, memory to your policy networks model itself. So resonance, which allow you to carry around information across very deep layers, allows you to, 1, add parameter or parametric complexity to the model while keeping around previous levels of representation in the same way resonance operate in CNNs. What we noticed, which was very surprising actually, is taking this simple change, which is basically just a few lines of code, and applying it to any of the existing methods results in out-of-the-box improvement throughout. So take any of your favorite gym tasks, take a favorite algorithm, and it works better. It works better in states, it works better in images. And it was not a fluke only in OpenAI gym tasks. If you do harder robot-style tasks where you are actually making robot manipulators move, the same thing was observed throughout the sort of spectrum. And in most cases, we actually found that as the task became harder, the performance gains became larger, which is very interesting. So the big picture takeaway here was that in robot learning, applying deep reinforcement learning as it is or in a vanilla fashion seems to be very suboptimal right now. We really need to think about where we can have particular kinds of structured inductive biases and where we can apply understanding of the domain to get better efficiencies and transfer. Now, one might argue that this was just simple tasks. When it turns out that we look at more complex planning or compositional tasks, it turns out that having or the need for this structure becomes even more prominent. I'm not going to get into all of details today in this kind of work, but what we have found is methods which are trying to do hierarchical tasks, either directly or through imitation, should and must take advantage of compositional hierarchy of both the input and the structure of the task. And we have done this over the last 2 years or so in multiple different instances. This is a model-based reinforcement learning kind of setup where we apply this idea of structure to the model itself. We argue that the model is hierarchical, which is operating at the level of abstractions. So say you're trying to go to the airport, you don't plan in footsteps. You plan in get to the train and then take the train to a certain station and then maybe get off or go to the highway and do this high-level abstract action. So we learn this model, hierarchical model, explicitly. Notice all of this is done in an unsupervised manner. So you don't actually get any abstraction labels. This was a choral paper. We also have worked on the ideas of converting decision-making problems into planning problems, where you can do this as program synthesis, or program induction rather, and allowing that enables you to directly predict sequences of tokens as a program. We have improved on these lines of methods since by actually inputting particular kinds of graph structure in the model itself, rather than a simple RNN predicting the next program in sequence. But the big picture takeaway in all of this was that both at the level of low-level control and planning, having understanding of the right structured inductive bias, both in the planning algorithm and at the input-output level, enables this kind of generalization. Now, what I've shown you so far is not necessarily optimal solutions to these problems. But what I've shown you actually is, or what I really hope to have shown you is, there's a lot we are leaving on the table. The next set of questions we should be looking at should be inquiring these biases. Now, what I'm going to do in the next part of the talk is to figure out what could be a solution to these sort of biases. And I argue that could be causal structure discovery and usage. So let's start with a core problem in this setup. One of the core problems in robotics often is data. If you were sort of noticing, as we started with sort of visual-motor skills, we have millions of data points because it's just a simulator. We go to planning problems, you get smaller data sets. Then you get to structured tasks, videos. Data set grows even smaller. But to do any sort of meaningful tasks from procedural, let's say, videos, or to do cooking eggs or cleaning homes, we really need large-scale structured supervision. Without data, we do not hope or have no hope of generalization. Now, data-driven robotics, particularly where data is from imitation, is not necessarily possible. This is just very recent examples of some of these ideas. We know imitation helps. We know it can speed up tasks and perform tasks where pure RL is not possible. But all of these examples lack the scale of data. The data here was maybe 20 minutes of data, while what we are talking about is hours. Now, if we look at our sister fields in vision and in language, they are really operating at the limits of supervision to a point where we have to figure out if our compute can handle such data sets. So robot learning is yet to witness this sort of data-driven success. Why? Data doesn't actually exist. So the first thing we have done is to actually build a pipeline to collect this data. And what I'm going to do today is to actually talk about, one, how to collect this data, then how to use this data, then figure out, can we do better causal discovery in this data? And finally, as practitioners of robotics, we need to be able to show that I can actually do some sort of realistic robot learning or safety to close this loop. So let's get started. The first question is, if you had the data, can you do something interesting with that? So this is a line of work that was published last year at ICRA, where first, we actually collected a lot of simulated data set with a platform called Robotics. The basic premise of the system is robotics doesn't have large-scale data because collection of data is very hard. We do not have crowdsourced mechanisms to collect this data. So we want to be able to collect very large-scale data in a manner that is very natural. So we built this system that allows arbitrary crowd let's say, workers to give you simulated and real-world data. As a pilot, we were able to collect about 5 or 6 days worth of data and about 1 day of platform usage. At the time, this was 10x larger than any other data set. Now, of course, the question was, can we do anything meaningful with this large data set? Or are any of our, let's say, robot learning algorithms able to learn from these external experiences? Now, the problem in simply stated is, you have a large set of demonstrations, you have to do some sort of learning, but you are not allowed to interact with the environment during the learning. You can only interact with the environment during testing. Now, it's not that batch RL or offline RL has not been implemented so far, but this was actually very interesting that this was the first time we were doing this at scale for robot manipulation, where the data was really hard, for hard tasks, not just pushing. And the data was really coming from humans, not just explicitly coded algorithms, and there were no rewards or very sparse rewards. What are the problems? The problems with real humans are very real. People fail in interesting ways, and people also succeed in interesting ways. It makes the data extremely multimodal. So any sort of algorithm that you're going to use downstream, let's say you're trying to copy actions, would not work because people don't have the same actions all the time. Different people solve the same task differently. So we have to learn a model that can actually use this data, because any sort of large-scale data will have these properties. So now what we do is we go back to an argument that perhaps copying the full trajectory is not a good idea. The intuition goes something like this. The model should figure out what it needs to do at a high-level goal selection and a planning level itself. The low-level information can be used from the data, which is equivalent to saying that the human may be planning at a higher level of abstraction, and we do not actually know what they're planning for. But if I look at very short snippets of their motion, then perhaps I can copy them, because those are unique. So what we do is, we are basically arguing that we can imitate small lengths of small snippets of motion, where we can have a high-level goal selection mechanism as a generative model, essentially, which can select a sequence of goals for the planner to follow. So this is essentially like a goal generator and then a goal following mechanism. The goal follower is trained directly on the robot data that you get from humans. The goal generator is only using the states, not necessarily the actions. Now, at the test time, what happens is, given where you want to go, the planner can first generate a few sequence of goals that are high-level states that you would want to reach. For each state, you can now figure out what is the low-level mechanism to get there. Now, of course, because you have essentially a generative model, can have many different goals, which you can then select based on the value function to get there. The value function can be dependent on some sparse reward model that you have, or just the action cost. Any questions so far?
Good. So I have a quick question. I guess you sort of took a U-turn in terms of what you did in the very first project that you talked about, where you were trying to leverage self-supervision schemes to learn better representations. But now it seems like you're advocating more of gather a lot of data, but then learn, come up with a
Okay, so let
learning
me
technique
answer that. I am still of the opinion, and I will show you a result. I'm arguing that the state representations and action representations should be self-supervised. The policy does not need to be self-supervised. And this is what we're doing, right? We're learning the policy here, and I will get to it very quickly, actually, where the state here can still be self-supervised. I will show you an example here. So these were the three sort of setups where one is a very simple sort of toy task, one is block lift, and another one is the more realistic sort of bin picking and placement task. In the interest of time, what I'm going to show you here is basically comparing it with state-of-the-art methods in imitation learning, pure behavioral learning, and then BCQ. BCQ is, or at the time was, a state-of-the-art batch RL method. We basically found that with reasonably large data set, you can have reasonably high performance out of the box without actually interacting with the environment. This is important to understand because if you can get a policy operating at 80% success rate, even before deployment, then you can fine tune it when you take it to the real world, rather than going from 0 to 80, which might take a lot of time and failures on the real world. In harder tasks, we noticed that the performance dropped, but the relative ordering between baselines and our method still remained. Now, to answer Krishna's question, why are we not using self-supervised representations? We are. We solved this problem in states earlier. Now we actually took it to vision, and we say, okay, let's train self-supervised key point-based representations in this setup and purely train the model for doing exactly the same task, but now in key point-based models. And we noticed that performance actually improves in this image-based representation. We can get up to 45%, if I remember correctly, purely from images. So qualitatively, this method works much, much better and much more sort of smoother and can do feedback control because you have a goal. So I have about 12 to 13 minutes left. I do want to cover at least the next two steps. So the next question, which I believe is the introduction of causality here, is the question we were asking was, we have a lot of data. We have shown that if you have data, you can learn some sort of batch or offline RL algorithms. Can we do any better? Let's look at a simpler task. Let's think of two balls bouncing around on a billiards table. The question we were asking is, if you get a lot of data like this, decision-making in such spaces, can you do better by thinking about data augmentation in a manner which is causally correct? So people have worked on data augmentation, particularly in reinforcement learning in the last year or so, or last few years, both in terms of states, where HER is hindsight experience replay is a very popular and prevalent method. At the same time, we have seen in recent times, people have done data augmentation in image spaces and have found a lot of gains to be had. But of course, there's no principled approach to do that. So one of the methods or one of the objectives of this effort was to actually unify this idea. So we wanted to create a generic data augmentation pipeline and say, when is data augmentation valid versus when it is not. In this particular case of goal relabeling and visual data augmentation, what you see is you can relabel goals or you can change data from the past if the data is completely conditionally independent from other aspects of the data. This notion is causal independence or local causal independence. In both goal relabeling and visual data augmentation, the problem was chosen such that it happens inadvertently. But in our case, we want to explicitly make and discover such causal independences or local causal independences, and then use this to augment data that would be technically or dynamically feasible. or counterfactual reasoning. So what is the problem? The problem here is, to do this, technically you need to build model, but model-based RL can be very tricky because you have to now learn the true underlying model. So can we do this differently? Can we do model-free relearning by stitching together environments? This is possible in some cases if data, the way you are trying to estimate the data, actually is separate. Now the problem is, are the causal relationships actually sparse? But it turns out that if you try to do global causal modeling, it's not necessary that the relationships will be sparse. For example, in this case, you can assume the balls are bouncing around. Now the question is, can I create this counterfactual example? And would this counterfactual example be correct? In this case, it will be correct because the blue ball and the orange ball are never interact. Now, on the contrary, if I create a new example where they are actually interacting, then this new example will not be correct because I cannot say with certainty that that the behavior will be will be as I predict. So I can only keep one of the examples while the other needs to be discarded. And I need to identify which one of those I need to discard. So what this call is essentially causal local modeling. So I have to understand how the data is being generated. I need to understand which parts of the system can be causally independent, and then I can do counterfactual modeling in the locally independent models. How do I identify such systems? What you can do is a very simple setup. You can learn these causal models locally as simple dynamics. You don't need to actually learn full dynamics model. All you need to learn is block independence in Jacobi. So let me explain how that works. So let's assume you're operating with very simple two balls. The features are position and velocity. So you have two balls, each with four-dimensional features. Now, the causal independence is given by an adjacency matrix across time. So time step t and time step t plus 1. If the matrix is block diagonal, then I can certainly say that orange ball is independent of the blue ball. Any questions on this? So I'm basically doing, in a way, some decomposition of the Jacobian matrix. So now this allows us a framework to add new data to what I've seen so far. So we start with a very simple domain, let's say a Pong domain. And what we see here is, if you get data of a certain data set size, and you use that data to do batch RL, and that's the performance that is reported. And you add new counterfactually valid data to this setup. What you see here is, by adding new data, or by thinking about data more efficiently, you can get performance that is 3 to 5x more efficient in using the data. So you can get the same performance at, let's say, 50,000 data points that you would otherwise get at 100,000 or more. And in the limit, you can actually get the same performance at 100,000 that you would have otherwise gotten at 250. And of course, there's a limit to this performance. You cannot infinitely add data, because then you run into covariate shifts, because there are parts of state space you have not seen. So you see this sort of leveling off of performance at 3 times the data set in this particular setup. A similar idea is also, or similar performance gain is also observed in, let's say, manipulation domains, where robot gripper is interacting with these objects and pushing around. And you see at least 2x gains in terms of sample efficiency in multi-goal RL setups. So now, the last part of this question would be, we started with data. We said, okay, we should do batch RL. It makes things efficient. We can do even better causal data augmentation if I can discover the causal model. So the next question would be, where are these causal models going to come from? Can we discover them in more complicated domains than the ones that we have seen so far? So for this one, let me describe a very simple game. The kind of things that we might want to solve are not just balls, but more interesting, let's say, cloth folding. So Let's play a game. We have about 7 minutes, and I think that's more than sufficient to play this. How about you guess the model? Everybody just think about what the model of this world might be, and then we'll use that model to do control. So this may be one ball bouncing, maybe on a flat surface, and no damping because the ball doesn't seem to be slowing down. How about this one? So it's 3 balls in a box with perhaps no damping. So now I'm making the balls independent, slightly more complicated. So it's 5 balls. So I was just playing around. Actually do this. Carefully look at the balls. Sometimes they change direction without actually colliding with anything. Now, what might be happening here is it's 5 balls. They seem to be different, but they are with unknown connections. And the model is trickier to guess because there are underlying connections of mechanisms in this. So they're not just like freely moving balls, but they are arbitrary connections, maybe rigid, spring, string, or no link. And these are latent mechanisms. Realistic physics actually has these latent mechanisms that you don't get to observe. You can only observe these variables, but not know what the underlying mechanisms are. And you need to estimate these mechanisms to predict future. 1. 2, you cannot memorize because any new graph or any new instance may have a different adjacency matrix. So you cannot just memorize this. So a simple interaction network will fail. Now, we looked at the balls example, but what about clothes? In the balls example, the state was given, but now if I argue that for an item of clothing, the state is not even given to you. So you can say, okay, if I'm required to fold a shirt, I can come up with a policy. I've seen this before. But what about a pant or a pant shirt suit? And how do we learn these models without explicitly doing this for every topology of a clothing article? If you think this is easy, have you looked at women's clothing? I do not know where to get in. So folding them is actually tricky because you don't know which side is up, which side is flat. So now you really need to figure out what is the connectivity pattern, which is basically equivalent to causal discovery. Why do causal discovery? 1, purely the argument is reinforcement learning tries to memorize this, while analytical physics model requires one specification to maybe actually too much of an overkill. You don't need full finite element model to actually fold the shirt. So what we have done is, and I'm going to skip some of the technical details in the interest of time, is we learn a self-supervised model of the representation first. So we represent the scene in some keywords. Then we learn a generative model, a graphical model, on the set of keywords. This graphical model has directional edges, which makes it possible. And then we use this dynamics model to predict time or predict space across time. It is important to have properties on these edges, which makes it what you would call mechanism. So a spring can have different spring lengths. That would mean that the edge just doesn't exist, but actually has properties. It may not be a spring, it may actually be a rigid rod. So the spring can act, the edge will have categorical properties as well. So just to give you a sense, the representation, the perceptual representation is trained purely through self-supervision end to end with a reconstruction objective. Once you have this, you fix it, and now you train the causal model or causal discovery model. We do this in different domains. One is the simple ball environment, because the states are easy to sort of evaluate. And then the fabrics environment, where, well, the output is not so easy to evaluate because there is no ground truth. So let me show you some results on very simple balls environment. In this case, what you see here is the ground truth graph of data being generated. And then this is the predicted graph. On the top right, what you see is if I only show you first 10 frames of the ground truth, and then you keep predicting key points. And then at the bottom is this predicted key points if you were to actually put the real balls on there. The same thing can now generalize, of course, to more balls. Performance degrades, but the fact that this is a causal model allows you to do this without any additional training. More interestingly, because this is a causal model, you can do extrapolation, and prediction. So you can train on a particular setup and then test on new spring relations or new lengths of rigid rods. And as I said, because this is a causal model of unknown edge types, a simple interaction model will fail, while a causal model will sort of have a much better performance. So I think a more interesting result would be this one, where you can have you can have the same model predict the dynamics of different kinds of topologies. So we start with a towel, same budget. So the budget here is 10 key points, and you learn a dynamic model that you can use to predict future. In this case, these are 2D key points. Same model can then be used to do pants, shorts. You can change the fabric type, so from cotton to nylon, and shirts. It is important to note that it's all the same model, which is the main sort of update from prior world, where you can now predict physics for new objects using this causal model with a singular system. I think in the interest of time, I'd like to sort of bring this to a close without getting into the last mile of the problem. So we talked about a number of things today, but I really hope if there's one thing that you take away from today's talk, this is to do decision-making in robotics particularly. The methods that we have been using have yielded very interesting results, but are nowhere close to our counterparts in vision and language. And that is in part because we have not correctly identified and discovered the correct inductive biases that help us make decisions. Two, one of those correct inductive biases could be causal discovery, because doing so enables us to interact with the environment and be sample efficient and achieve generalization in the form of, let's say, uncertainty quantification out of the distribution generalization, or being able to do counterfactual generation that enables sample efficiency in usage of it. So with that, I would like to thank a number of people I've worked with over the years, many of the students without whom none of the robot videos would be possible. And thank you for my previous lab, where a number of this or much of this work was done. And finally, thank all of you for the privilege of your time today. And hopefully I can answer some of your questions. I'll still have time. So thanks a lot.
Amazing stuff, Animesh. It's like unbelievable how much the breadth and so many, like, yeah, so many, I think, really, really interesting insights there. I have a few questions, but I'd rather defer to the. I want to be cognizant of your time. We're a little bit over time, but
I can hang around after this, but feel free, sort of, if the folks on the call have questions, or in the chat.
Any other questions?
Yeah. So I was actually wondering when you're talking about the last work that you presented on causal discovery. There's been some work recently in the ML community, particularly on equation discovery, and I'm wondering if you had any thoughts on those lines of works, like explicitly discovering equations versus having these dynamics models, which may not necessarily be explicit. Do you see, like,
so our work is beyond, I would say our work, or at least our efforts, were somewhere between pure intuitive physics, which are, let's say, ML-based data-driven models, to full-on symbolic regression. So in one sense, symbolic regression and our method are basically very similar methods of solving the same problem, but looking at it slightly differently. Symbolic regression requires you to generate the basis functions, and then the regression model is basically figuring out how to compose them. In our case, we want to do this purely from data, but we do require that the model has minimum description length, which is basically what it makes it sort of this causally structured. Causal structure is important because that allows composability and counterfactual reasoning and interventions at particular edges. But at the same time, one thing that we want to differentiate is we want to look at these problems purely from a robotics perspective or decision-making perspective. So the input needs to be not featureized. So the input needs to be images or analog features or analog, let's say, streams of data. So you do not know explicitly what is a good state representation. So if I know, for example, what are the homogeneous coordinates of an object, then q dot, then writing equations in q dot is easy, but writing equations or differential equations in image spaces is trickier. And I think that's where we want to or need to go to. Going forward, I think what will happen is you will start connecting causal models with state representation learning such that you build causal models, but only of sufficient parameters. So there's a family of tasks you want to do. There are only things that you need to track, and only those things need to be sort of causally modeled. Everything else is back.
Makes sense, yeah.
Other questions? I think I'm going to end.
I have a
go ahead.
question, but I was just like, I didn't want to hog all of the time. So sure, yeah, maybe I'll just go with one last question. So particularly when you talk about like physics or learning models of objects in the world, there is definitely a gap between all the things you can model versus like the real world. Do you see kind of these key point based methods generalizing to real world tasks, or like are you in the process of trying them out on real world sequences?
Yeah, I'm thinking about answers in a manner that is the most meaningful. Short answer is yes. We are already at this point gotten to a point with results where I did not describe, taking these ideas of, like, say, causal models from 2D to 3D and do this. The question that you asked actually is deep. Your question is key point based representation or self-supervised key point based representation sufficient for real world tasks? If I were to answer that in a short sort of quip, the answer is yes. There are real world tasks where that is sufficient. One example of where this has been successful is folks from MIT, Russ Tedrick's group, did a bunch of work with key point based representation. Is it sufficient for all tasks? No, because you can always ask, give me the red cup. Key points don't capture the notion of red. So you may need better representations for a different style of tasks. There are many tasks which are purely positional or position or pose based. That can definitely be achieved with pure key points. You can very easily, this is something because we have done this already, adapt the key point based representation to also include visual information. This is learned because you have to use the key point based representation to reconstruct the image, and then you can actually do more interesting visual tasks. One of the things that we have worked on, and I did not get a chance to present, is, let's say you are trying to hammer. You learn a representation of the hammer as key points. So key points will give you just the representation of what you would call the shape of the hammer. But what if I was adversarial? I flip the density of the head and the handle. So I change the texture. Unless I have that representation, my policy will learn the absolutely wrong thing. So that is something that we ended up learning, where you can actually flip the model, and the key points with contextual information or contextual texture-based information will also learn the right thing. So in principle, there's a lot of promise in this direction, but at the same time, newer 3D representations like SDFs or NERFs also have some promise, but personally, we have not yet tried them.
Okay, thanks.
Okay, I have a question, but I want to ask it off stream, so I'm going to end the stream.
Sure.
Okay.